Okay, so let's start this exam review. And as is my custom, I'll actually do this in reverse order. So let's talk about the last subject we have talked about. For the last 10 days or so, what are we talking about? We're talking about how to create a magnetic field, right? So we're basically talking about sources of magnetic field. And conceptually, what's the summary of this chapter? I would say the summary is that currents or moving charges cause magnetic fields, right? So currents cause magnetic fields. And I had two strategies to determine the magnetic field created by any current distribution. What are those two strategies? Amperes law and Biot-Savart's law. So what did Amperes law tell me? Amperes law told me the following: if I have some currents, what I need to do is to define a loop around them. On this Amperian loop, if I integrate B dot dl, what I will find is mu0, a universal constant, times I in the current, total current passing through my loop. But let's be very careful. I in has a sign convention, right? Your currents may be going either in the sense of the circulation of your Amperian loop, or they may be going opposite to that. So you have to take care of whether you have positive currents or negative currents. All right? What's the other strategy to calculate? That's right. Biot-Savart. And this was more microscopic. If I had some current carrying wire I can take a small section on this wire, dl, and I actually can ask what's the magnetic field created at a point that's a vector r away from this small current, and the answer was dB is mu0 over 4 pi times I carried in the wire, but then there was this really nice factor dl cross r hat divided by r square. R hat just told me the direction from the current to the observation point. Now, question, yes?
Can you please tell me, like also in the future, can you tell the rule that you apply with your and the cross product rule maybe?
The cross product rule?
The cross product.
Okay, so the cross product rule, maybe let's review this because it has a lot of bearing on that. If I have two vectors, A and B, A cross B, it has the following property. First, A cross B is perpendicular to both A and B. Okay? What does that mean? Here is my A vector, here is my B vector. How can I be perpendicular to both of them? Now, if I'm perpendicular to the first vector, I will not be perpendicular to the second one. If I'm perpendicular to B, I won't be perpendicular to A. Which way can I, how can I be actually perpendicular to both? I need to get out of the plane. Okay? If I'm out of the plane, I'm perpendicular to both. But now I can be out of the plane two ways. I can be either coming out of the plane or going into the plane. So I need to determine which way is correct. Okay? So the sense is given by right hand rule. And how do I apply the right hand rule? I take my 4 fingers. If I'm calculating A cross B, I put my 4 fingers onto the first vector. I still have the freedom to rotate my palm. Okay? I rotate my palm so that I can close my fingers towards the second vector. So A cross B gives me, apparently, coming out. Okay, so that's how I use my right hand. That's my definition of right hand rule. There are equivalent different ways of doing the same thing. So apparently A cross B is coming out of the plane. How about B cross A? B cross A, that's another important thing to remember. A cross B is minus B cross A. That's it. Just in the opposite direction. Okay. Let's try it. B cross A. Now that we can do it. Here is my B, the first vector. So with my 4 fingers, I'll align my hand so that I close my 4 fingers towards the second one. So B cross A is into the board. Okay. Be very careful. Most of you are, how many of you are right-handed? Most of you are right-handed, right? That's a given. The worst thing is in the exam, and you have been trained for the university entrance exam, where speed is a big factor. People do not leave their pen and do it with the right hand. There is a lot of tendency in the students to use their left hand to calculate stuff. And opposite, all the answers are negative of what they should be, right? That's a terrible thing, but that happens a lot, so be very careful. In the exam, you're not that much rushed for time. Leave your pen aside and use your right hand. For those of you who are left-handed, that's not going to be a big problem, okay? And incidentally, Maxwell, the guy who pretty much invented all the stuff we're talking about, okay? He used a left-handed coordinate frame. And if you try to read his original papers, first of all, he doesn't use the vector notation. He always writes things in terms of components. It's maddening, you know. He has minus signs in all the wrong places. So let's go back to our Biot-Savart law. For example, here, what will dl cross r look like? dl cross r will be into the plane, right? Now, are these laws both always valid? Okay, so there is an important distinction here. They are both always valid. Actually, if you're good with math, you can derive Amperes law from Biot-Savart's law, and you can do the reverse. You can actually derive Biot-Savart's law from Amperes law, which is a little bit more hard. However, as a calculational tool, when I'm trying to calculate a magnetic field from given currents, Amperes law is only useful when there is enough symmetry in the system. It may be valid, but it won't help you. That's always possible. Okay? E equals mc square is a valid physics law. It won't help you in the exam. It has nothing to do. That's not a bad joke. Come on. I mean, I'm feeling bad here, right? Okay, right. So now we have actually defined some very standard configurations for currents. One was that if I had a single wire, the magnetic field around it circulated in the sense I have shown. So that actually gave us the second kind of right-hand rule to determine directions. If I put my thumb in the direction of the current, here my fingers showed me the sense of circulation of the magnetic field, and I actually even remember the result, B as a function of R, is mu 0 I over 2 pi R. Okay? We have also talked about another very useful device that can create uniform magnetic fields. What was that called? A solenoid, right? So if I actually have a solenoid that has n turns per unit length, it creates a magnetic field B, which is uniform inside, and its value was just mu0 times n times I, where I is the current running in the wire. And how did I determine the direction of the magnetic field in the solenoid? I had my third right-hand rule. If I put my 4 fingers along the loop's rotation, my thumb gave me the direction of the magnetic field, right? So in this case, the direction of the magnetic field would be coming in. I don't know why I drew it like this, but it's going to circle like that. Not circle, it's going to go through like this. We have also talked about what happens if you take your solenoid and turn it into a toroid. We can again use Amperes law to calculate the magnetic field. We have talked about if I have a uniform plane that's carrying a current, what the magnetic field looks like. I think you should all be able to do those 4 cases to see if you can actually calculate the magnetic field for some given configurations. One more important rule we need to remember is that we have superposition applies to magnetic fields. So if you have, say, 2 wires, what should you do? Should you try to do Biot-Savart because there is not enough symmetry? No. What you should do is you should separately consider each wire. You can find the magnetic field by Amperes law and then add. One thing not to forget is that B is a vector. And that looks obvious, but you would be amazed how many students actually just forget and add up the magnitudes of B. All right? Good. Then I think that's pretty much what we have talked about. I mean, practically what we have talked about in this chapter. We have talked about more exciting things like the stones from Manisa, right? The magnets, permanent magnets. What was the thing we actually need to remember from that? The source of material magnetism goes back to atomic currents. There is, again, magnetic field is created by currents, but those are currents inside the atom. And most atoms have these currents, but when I have a macroscopic object, the currents of the atoms or the magnetic fields of the individual atoms may not align. That's why you will not see any magnetic behavior. And why do they not align? Because when you're at finite temperature, there will be a lot of fluctuation. Okay, these atoms will be jiggling. That's one factor. Another factor is that really the atoms may not energetically favor to be in the same direction. But for some materials like nickel, like iron, these magnetic fields of the individual atoms really like aligning with each other. And you'll actually have to learn quantum mechanics to see if they will like to align in the same direction or whether they would like to be perpendicular to each other or whether they like to be opposite to each other. There is a whole class of magnets which are very hard to explain. There are antiferromagnets. What iron and nickel are, they are called ferromagnets. They like to align. There are materials where you actually have opposite alignment between neighbors. These are called antiferromagnets. There are things called ferrimagnets where one atom has small magnetic field, the other has large magnetic fields. There are things called frustrated magnets, helical magnets. I can go over the list. That's why there is in our graduate curriculum, there's a course called quantum magnetism. So as far as physics 102 is concerned, I just want you to remember that the stones from Manisa are not magic stones. They just have these wonderful quantum mechanical atomic currents in them, okay? Which is sort of magic. But I'm not going to review more about that. What was the previous chapter? What was the chapter before that? We talked about magnetic field itself. And how did we actually know that there is such a field? Because it acts forces on currents and moving charges, right? So again, we have two important formulas to remember. If I have a charged particle that's moving with velocity v in some magnetic field B, it is going to experience a force F, and F was Q times V cross B. So it's going to be perpendicular both to the magnetic field and to the velocity of the particle. Okay. Two things you need to remember about this formula. One thing is that if I look at the trajectory of the particle, it's going to go around in circles, okay? So, and the radius of the circle will be larger if the velocity is larger, but amazingly, the time it takes to complete one circle does not depend on the velocity, okay? And that actually made us define something, the cyclotron frequency, QB over M. But that's easy enough to calculate without actually remembering this formula. Just remember that these particles circulated under a magnetic field, and positive and negative particles circulated in opposite senses, right? Positive particles, if they are circulating clockwise, the negative particles will be turning counterclockwise. Right. What other formula did we have? Instead of charged particles, if I actually have a wire carrying current I can take a small section of it with this vector dl, which is oriented along the wire in the direction of the current, and if it's in some magnetic field B, there will be a force acting on this small section, and this force, of course it's going to be a small force because it's a small section, will be I dl cross B. In practice, what does that mean for a uniform wire of length L? I can define a vector L. The total force will be I times L cross B. All right? But the real formula is for the differential part, so we can actually do it for a not straight wire, but any kind of curved wire. All right? Now, one type of problem that we have not maybe spent enough time on in our lectures, but that may come up in the exam, is combining the knowledge of these two chapters. Okay? For example, here's a straight wire, and here's another circular wire. This is carrying current I1. The distance from the wire to the center of the circle is R. This is small r, and this is carrying a current I, and the question is, what is the force on the loop? How would you do this? How would you do this problem? Now, this question has two parts. This straight wire is going to create a magnetic field, and that magnetic field is going to create forces on the loop. So I have to do this in two steps. So what would I do? Calculate B of R by Amperes Law, and then calculate F by taking small sections on this by integrating I dl cross B. Can you guess which direction the force will be? Let's see if you have actually formed an insight into this magnetic field. Let's see. Here, the current is anti-parallel to the wire, right? When currents were anti-parallel between straight wires, which way was the force? It was repulsive. When currents were carried in the same direction, the force was attractive. So left-hand side of the wire is being repelled. Right-hand side of this loop is being attracted. Which force is larger?
The repulsion is larger.
Why? Because the magnetic field there is higher, because it's closer to the wire. So I would expect this wire to be, this loop to be repelled from the wire. We could probably calculate it in 10 minutes, but let's keep with this our review, all right? But that's a good problem to solve. What else did we say about the magnetic field? Not much really, right? We've actually said it was discovered in Manisa. I keep saying that. I don't know why, but I like it. I haven't visited Magnesia ancient city yet. I hope to do that someday. Now, we have actually said one more thing which was somewhat important. We've talked about exactly what if I have a current loop. Current loop in a uniform magnetic field. So, if I have a current loop that's carrying a current I, and it's put into a uniform magnetic field B, I define the quantity which I call the magnetic moment, magnetic dipole moment of the loop. And how did I define that quantity? I said mu is just the current carried by this loop times A, where A is the area vector. How do I define the area vector for any general area? Well, first of all, the magnitude of the area vector is the area in meters square of that section. But there are two possible directions. If I have any area A, let's say this surface has area A, my area vector may be looking one way or the other. How do I resolve which way I will actually choose? I will take my four fingers and circulate them along the direction of the current. That will give me the area vector. So direction by right hand rule. So my area vector will be like this here. And what will be the force on my loop?
0.
the total force in a uniform magnetic field will be 0, but there will be a torque. Torque on my loop will be mu cross B. Alright. If let's say this is my current loop, if this is my magnetic field, I will see a torque which depends on the angle. But if I keep the magnetic field constant, the most I can get out of the system is that there will be oscillations in the direction of my loop. But what happens if I actually change the magnitude of or the direction of the magnetic field? If I change the magnitude of the magnetic field, I can actually change the direction of the torque. I can go positive to negative, negative to positive. And if I actually do that nicely, I can get an electric motor. I can get the loop to rotate constantly. Okay, that's the basis of the electric motor. And also the generator, the next thing we're going to discuss starting on Wednesday is induction and how you actually do the reverse when you actually move conductors in a magnetic field. You get currents. Okay, so there is this three-way thing. One is that magnetic field gives forces on current. The second is that current creates magnetic field, and the third thing we are going to learn is that change of magnetic field creates current. So this three-way thing is going to be quite important, this three-way relation between magnetic field, force, and current. Right. Good. How about before that? What did we talk about? We talked about DC circuits. And to be able to talk about circuits, we need to talk about circuit elements. What are the components I can put in my circuit? Okay, the simplest one is maybe the resistor. Or maybe even simpler is a battery. Okay? Now this is an ideal battery. Okay, we've talked very briefly about a real battery. A real battery, this is an ideal battery, and it's good because a real battery, the guy you actually buy for 5 Turkish liras at Meteksan, will be almost like this. It will be an ideal battery with an internal resistance. And if you actually do not pay 5 liras but 100 liras, you can get a battery with less internal resistance, which is closer to an ideal battery. That's why battery prices may change a lot. What else? What kind of circuit elements am I allowed to use? I can also use capacitors. Good. We will learn about other circuit elements like inductors in this course, and those of you who are in electrical engineering will get to enjoy even more circuit elements than that. Now, nonetheless, all DC circuits depend on two very simple laws, right? What were those? These are called Kirchhoff's laws. And the first law was very easy. Whenever I have a node, so more than 2 wires meeting at the same point, the total current coming in, I1 plus I2 plus I3 is equal to 0. This was called Kirchhoff's current law, node law, right? Why is that so? Why is the total current coming into any node 0? What would happen if it was not 0? Charge would accumulate at that point. Current is just the flow of charge, right? And we don't want that. That's not what happens in an electrical circuit. Charges go through loops. They do not actually accumulate. They do not keep accumulating at the same point. If they accumulate, after a while there will be so much electric field no more electrons would be able to come near them, right? So that's the first law. How about the second law? It actually told me that no matter how complicated your, I don't know, circuit is, I'm trying to draw a complicated circuit in a short time, so I don't know what I'm drawing also. Okay. Another capacitor and then a resistor. I don't care how complicated your circuit is. If you take a loop, any loop here, sum over voltages over a loop, voltage drops over a loop, must be 0. Why is that? Well, that was a definition of our potential, right? We could define a potential only for conservative quantities, and electrical forces are conservative, so no problems. This is going to be on YouTube, so you don't have to, take a picture all the time. I'm also putting them on the PDF files onto Moodle. Now, what did this tell us in practice? It told us that we could analyze any circuit we want with these two laws. But most circuits can be reduced to simple elements. For example, if I had two resistors, R1 and R2, in series, that was equivalent to a single resistor with R1 plus R2 resistance. And if I had two resistors in parallel, that was equivalent to sum of the inverses of these two resistors. How about for capacitors? For capacitors, the rule was reversed. If I have C1 and C2 which are in series, then C equivalent inverse would be C1 inverse plus C2 inverse. And if I had two capacitors in parallel, then C equivalent was just C1 plus C2. All right. And you may say, hey, okay, what happens if I have resistors and capacitors together in a circuit? So we have analyzed two circuits here. One was, if I start with some charge on my capacitor, how it discharges over a resistor, right? That was the discharge of a capacitor. What did we find? We find that this discharge follows an exponential pattern, right? We could scare ourselves saying that we are solving a differential equation, or we could just remember that exponential is the only function that's constant under derivatives and integration. Okay. So what was tau? Tau was
RC.
You're right. Tau was RC, which is called the time constant of the circuit. Generally, tau is what you see dividing time in the exponentials. Okay, it doesn't have to be RC all the time, but when you have a exponential behavior in your function with e over t over tau, that tau is defined by the exponential function itself. Okay. We've also looked at how a capacitor initially uncharged would charge over time if I have a resistor here. Okay. And what did we find out? We found out that the charge here will go to its final value, V over R, again in an exponential manner. All right? And here tau, not V over R, it's going to be V times C. Okay? Tau again is going to be RC, time constant. And here was also a good rule. Whenever I have a capacitor in the circuit, if I wait for a long time, when t goes to infinity, it just becomes an open circuit. If I wait long enough, the capacitor will saturate to its final charge. No more current will be flowing on it. So it's easy to analyze the long-term behavior of these capacitive circuits. Okay? Good. Now, what did we talk about before the DC circuits? We talked about current and resistance. And what did we say? We've talked a lot about the microscopic picture of what happens inside the resistor. But at the end of the day, we came up with this nice formula telling me that if I have a cylinder with area A and length L, its resistance, so the current is coming in and there is a voltage V, the resistance will be proportional to resistivity of this device times proportional to the length and inversely proportional to the cross-sectional area. This was a material property called resistivity, and this was R is basically V over I, the resistance. The unit was ohm. Now, what was current though? Current, how did we define current? It was the total charge passing a plane per unit time. So we said it's dq dt, total charge passing a plane. But we also gave a more microscopic definition of current. Instead of current, I could define something called current density, J, which was proportional to the density of electrons or charge carriers at some point, their charges and their net velocities. So this was going to be a vector field. If I have a non-uniform conductor, J would be a vector field. And the flux of this vector field, J dot dA over any surface, will give me the current passing through that surface. Okay? It was like electric field and electric flux. And on Wednesday we'll define magnetic flux. So for any vector field we can define a flux. For current density we have current as the flux. We also said two more things. If I have a resistor here which is running a current I, the power dissipated on the resistor, the power that's being turned on the heat in this resistor was R times I square, or just as well V square over R, right? How about for a capacitor? What's the power dissipated on the capacitor? There is no dissipation over a capacitor. Capacitor, an ideal capacitor, is a device which stores energy and then releases it back into the circuit. So instead of this power dissipated, we have said if there is a voltage V here, there is a energy stored inside the capacitor, which was 1/2 C V square, or just as well 1/2 Q square over C. How about the relationship between current and voltage? For the resistor, voltage was just I times R, but for the capacitor, it was better to remember I, which is dq dt, is C times dV dt. So the current coming into the positive terminal of a capacitor basically measures the time derivative of the voltage across the capacitor. All right? And that brings us pretty much to the first midterms topics. Now you should all realize that there is really no definite distinction between the first midterm topics and second midterm topics. Obviously, the second midterm is going to focus more on our recent topics. However, that doesn't mean that you can forget about Coulomb's law. You should not forget about Coulomb's law ever. But for the second midterm, you'll need it more than for a regular day. Remember Gauss's law. Gauss's law, for some reason, was not tested at all in your first exam. Okay, it's quite conceivable that it will be tested now. Right? Why are you so? Everyone has panicked. Of course, why not? Unfortunately, I even if I wanted, I wouldn't be able to see the questions. That's how it works. Okay. Now, don't panic. Okay, the Gauss. I don't know if there's a Gauss law question, but you should remember how to use it as well as Amperes law. But here is the thing: we have 2 hours on Wednesday, and I'll try to make myself as available as possible to your questions. Although I want to talk a little bit about induction, we'll keep that short. And maybe I'll stick around for the recitation hour and try to answer as many of your questions as possible. Also, you can come to my office and ask questions. That's possible too. Right? See you on Wednesday.